Alright, so we continue to look at integrals involving forms that evaluate as arcsine or arctangent. We just saw one at the end of the last video that evaluated as arcsine. So if we look at this one, again, I see the square root in the denominator and I say, hey, that's going to look like arcsine, right? In fact, I got the square root of 1 minus, instead of x, I've got a t. That's okay. That looks perfect. That looks perfect. But the problem is up top, isn't it? Here we have a dx, and here we have a dt. It should be 1 dx. Instead, I've got t plus 6 dt. Well, that's a problem. The problem is that t. Now, if I can get rid of that t, if I just had the 6 up there, that 6, if it was just 6 by itself, that's 6 a constant multiple. I pull the 6 out, I'm left with a 1. I'm done. It's just 6 times arcsine of t. If it's just a 6 up there, right, it's just that. But I can't really just subtract t from the top. I can't bring the t out. That t is a bothersome thing. Now, on the other hand, if it was just the t, t dt, right, just get rid of that 6 for a minute. If it was, I know it's not, but if it was just the t up there, no 6, what about that? I mean, it's certainly not arcsine because it's got a 1 up there, and I can't do anything with that variable up there. However, this form is something we can do with simple, what I would say simple substitution, because the denominator has a composition. If I choose u to be the inner function 1 minus t squared, what's the derivative of 1 minus t squared? Derivative of 1 is 0. Negative t squared would be negative 2t. Well, I would have du is negative 2t dt, and I can adjust that by multiplying by negative 1/2 to get t dt, and it would evaluate as a 1 over u integral. Or sorry, 1 over the square root of u integral, excuse me, which is u to the negative 1/2 power, which is just a power rule. So, man, if it was just a 6 up there by itself, I'm good. Arcsine, right? If it's just the t, it's a simple substitution. I've got a u to the negative 1/2 basically to integrate. But it's t plus 6. So, what can we do? Well, they say that breaking up is hard to do. At least there's a song written about it. I don't know if you know about it. But for us, it's not too bad in calculus to break up. Of course, we're not talking about relationships. We're talking about breaking up this sum. And what I'm going to do is I'm going to do exactly that. I'm going to break this up into the sum of two fractions, t divided by the square root of 1 minus t squared, plus the 6 divided by the square root of 1 minus t squared. Right? dt. So I'm going to split it up. Right? Split up. This looks like sput up. Split up. Okay. Split up. We're going to break it up, right? And I can do that. It's a common denominator, right? I can add this back to here and I get the same thing. But I'm going to treat each of these separately, right? So again, this one here, as we said, this is just 6 times the integral dt 1 minus t squared square root, right? Which is exactly, right, the arcsine. So this one here evaluates 6 times inverse sine of t, right? Plus c, right? And we'll do the c at the very end of everything. But this one here, how can we do this one? This one here, notice I can let u, as I said, be 1 minus t squared. This is a little substitution now. And du, derivative of 1 is 0, negative t squared, negative 2t. So du is negative 2t dt. Now I've got just a t dt. This dt would be multiplied by it. And so multiplying both sides by negative 1/2, I'll get t, whoops, this is dt, excuse me, dt. du dt was negative 2t. And so multiplying both sides by negative 1/2 gives me this. And so this integral here becomes t dt is negative 1/2 du. I'll pull that negative 1/2 out over what? The square root of u. Square root of u. And what is this then? This is u to the negative 1/2. This is negative 1/2 integral of u to the negative 1/2. Right? 1 over u to the 1/2 is u to the negative 1/2. And this is just easy integral. This is a power rule integral. Right? So I've got the negative 1/2. I add 1 to negative 1/2, which gives me positive 1/2. Divide by 1/2 is the same as multiplying by 2. I get 2u to the 1/2. And cleaning that up, negative 1/2 times 2 is negative u to the 1/2, or negative square root of u, which is negative what? Square root of u, which is 1 minus t squared. Okay. So this integral, simple u substitution. I say simple in the sense it's not, we're choosing like we did when we learned the substitution. Use the inner function, 1 minus t squared under the radical there. All right, and I do have t dt up top, which is just negative 1/2 du. We get an integral that we can do, power rule, and then replace back to the t variable. Here, inverse sine. And so the final answer is that this integral, we evaluate this first one, evaluates as negative the square root of 1 minus t squared plus 6 sine inverse t plus c. So that's what we have to do sometimes, again, is to break up the integral into parts. In each part, if we could do those in separately. So remember, the integral of a sum of two functions is just the integral of this one plus the integral of that one, and that's the idea we made there. Now, that's, these are some pretty complicated ideas we've looked at, but don't get too, lost in it. Try and say every time that this integral has to be, something involving inverse sine or inverse tangent, for instance. We see, for instance, here, this is not inverse sine, right? This comes out to be, this, simple substitution. Same thing here. Is this integral inverse tangent form? So remember our inverse tangent form here, right? It certainly looks like it, but again, up top, it's not just a constant. It's 6x dx. And so the answer is no, it's actually not. It's a simple u substitution. In other words, now if I let u be the denominator, this time this will work because the derivative of x squared plus 1 is 2x. So du is 2x dx. I've got a 6x dx, so if I multiply both sides by 3 times 2, I can get everything to match up. And this integral then becomes 6x dx is 3 du, pull that 3 out, and the denominator is just what? U. Okay. So I mean, it wouldn't make any sense to let you say, well, it's like tangent form, choose u to be x. That's not going to help any. In fact, never choose u to be x. That doesn't really change anything. If u equals x, du is dx, and you just change the variable on the same integral. That's not going to do anything. But if I choose u to be the whole denominator, I get this form, which is what? 1 over u. What form is that? Is that a form we know? What's the antiderivative of 1 divided by u? That's the natural log integral. All right? Natural log of absolute value of u. Again, throw in plus rc. And so, anytime I see this form, 1 over u, I call that the log integral, the absolute log integral, or the natural log integral. All right? Go back to the original variable. Now, I do natural log absolute value of x squared plus 1 plus c, and that's fine. You can write it that way. I guarantee you when you look in the back of the book or you're looking at my answers, you'll probably see this. Some of you forget the absolute value bars, and so you won't even think anything about it. But some of you do, and you say, wait a minute, absolute value bars, where's your absolute value bars? I don't need them. Do you see why I don't need them? Look what we're taking the absolute value of. X squared plus 1. Can x squared plus 1 ever be a negative value? No. X squared plus 1 is always 1 or more. And so I don't really need the absolute value bars technically. Now, if you write it this way, that's fine. It's not wrong, but it's just not wrong to write it this way either. Okay. All right. So you've got to be careful with that. Okay. So that's all I'm going to talk about in terms of the inverse sine, inverse tangent. There's also integrals involving inverse secant. As we said, there's this form. And you can also run into integrals that evaluate as inverse cosecant or cotangent. I mean, these are tough ones, but I want you to focus on these forms, and that's what you'll see in the homework mostly. Okay. I do want to, in the next video, though, talk about one more type of transcendental function, and that is the general exponential functions. So we're going to look at those in the last video.